Welcome to this lecture series in general topology. In the previous lecture, we defined the notion of a basis of sets on a given set. Or in short, we defined what is a basis on a set. And in today's lecture, we'll discuss the topology generated by a basis on a set. And let us recall the relevant things. So what is a basis? X is any set, and let B be a collection of subsets of it. Then we say this collection is a basis on X if the union of all the things in it is the entirety of the original set. And if you find two members of this collection which intersect non-trivially, and you pick an arbitrary point in the intersection, then there is another member in the collection with this property, meaning it contains the chosen point and is contained in the intersection. So this was a rather strange looking definition, but we gave examples and hopefully it is clear, or at least makes some sense. This lecture will hopefully make it clear as to what is the use of it for us in the context of general topology. Okay, so we need to know what is meant by the topology generated by a collection of subsets. If you have a collection of subset C of a set X, then the topology generated by C is, by definition, the intersection of all the topologies on X which contains C. In other words, or in heuristic terms, it is the least expensive topology on X which contains C. A trivial remark is in order. If tau is the topology generated by a collection C of subsets of a set X, then every element of C is an open set in this topology, meaning every element of C is a member of this topology. Okay, the standard topology on the reals is same as the topology generated by the set of all the open intervals. And recall that, as we mentioned in the previous lecture, the set of all the open intervals is a basis on the reals. So I don't want to recall what is the meaning of this, but anyway, let's move on. We talked about the Euclidean as well as the infinity distance between 2 points in Rn. So if x and y are 2 points in Rn, then their Euclidean distance is defined in this manner, motivated by the Pythagoras' theorem. And the infinity distance was defined in this manner. To visualize them, we defined balls. So the ball of radius r centered at x under the Euclidean distance is the set of all the points in Rn whose distance from x is less than r. Pictorially, in R2, you would draw this picture. You will draw x and then a ball of radius r. Everything strictly inside this ball is this ball. And we, of course, draw the same picture for Rn because we can't draw anything better. Similarly, the infinity ball, you make the point x and make this square. And this thing is r. So if you draw a picture in R2, this is what you would be drawing for this object. And we also mentioned this, or rather we proved this for n equals 2. So this is a simple containment lemma. We proved when n were equal to 2 and gave this as an exercise for the general n. Okay, so with that, let us proceed. Here are some problems for practice. And now let us get started. Okay. So suppose we have a basis on a set X and let tau be the topology generated by it. Then we want to say something about this topology. It's just that you can generate topology out of any collection of subsets on X. But if you have a basis which you use to generate the topology, you have an extra handle on that topology, and this theorem is about that. So with that out of the way, fix any arbitrary subset of the set X. The following are equivalent. The first is that this is in the topology generated by the basis. This is one statement. In other words, or said differently, we can say that U is open in X under tau. This is another way to say the same thing. The second statement is U can be expressed as the union of some members of the basis. Right? So we are saying that these two things are equivalent. Saying that U is an element of tau is same as saying U can be expressed as the union of some of the members of the basis. This equivalence can be said in a different way. It says that one way to describe this topology is that you take arbitrary unions of the things in B. You pick whatever collection you want from B. You just choose some members of B, take their union. You do this for every possible sub-collection. What you get will be a topology, right? And that's what this equivalence is saying. Okay. So now lastly, we'll just restate this in a different way. The third one just says that for all elements in U, there is a basis element such that X is in B and B is contained in U. So this equivalence, the equivalence of 2 and 3, is a purely set theoretic exercise, and that I will not be doing. So this is an exercise. We will be establishing this equivalence. Okay. So once again, what does this equivalence say? It says that there is a description to the open sets under this topology. It's just those sets which can be written as the union of things here. The fact that this is a basis will be the key point. I mean, you can pick an arbitrary collection of subsets of X, and then no, you won't be able to say that the things which are open under the topology generated by that collection is precisely those things which can be written as the union of some of the members of the collection. No, that's not. You can't say that in general. Okay, so let's prove this. So proof of 1 implies 2, or proof that, let me define something and then I'll say. So let S, or let theta, be the collection of those subsets of X which can be written as the union of some elements or some members of the basis. Right? So that's our definition of theta. Note that theta is contained in tau. Why? Because every basis element is, of course, there in tau. Tau is the topology generated by the basis. Right? Now, since tau is a topology, and since every element of the basis is there in tau, anything that can be written as the union of things, union of some of the members of the basis, is also there in tau. Because any topology is closed under taking arbitrary unions. So anything in theta is there in tau simply because anything in theta can be written as the union of some of the members of B, which are in particular union of some of the members of tau, but union of some of the members of tau is again again in tau, and therefore this containment is there. So we will show that the reverse containment holds, which will prove what we want to prove. So once we establish that theta and tau are the same things, these two statements will become equivalent. And I'll let you figure that out if that is not immediately clear. So why this will imply that is an exercise. And now let's get down to business. And in theta, when I wrote theta, I meant to include the empty set by force. So here, the empty set is there by force. Okay. Some authors don't even do that. When they make this thing, it's clear by convention that it already contains the empty set, but there is no harm in putting it there by force. So now we want to show the reverse containment. Okay, so this is what we want to do, but to do this we will do even something little else, something little different. We will show that theta is a topology on X. And once we do this will follow. Why? Because once theta is a topology, and we already know that theta contains this guy. Why does theta contain the basis? Because clearly every basis element, if S is a basis element, it can surely be written as the union of some of the members of B, namely the member itself. So clearly theta contains the basis. And once we show that theta is a topology, theta therefore would contain the topology generated by the basis. The topology generated by the basis is the least expensive topology that contains the basis. Theta would then be a particular topology that contains the basis. So the least expensive topology that contains the basis should therefore be contained in theta. The formal argument would be that, what is tau? Tau by definition is the intersection of all the topologies that contains the basis. And since theta is a particular topology that contains the basis, tau is contained in theta because tau is the intersection of theta along with other things. Okay, so therefore our goal is now this green thing. Once we establish this green thing, we will be done. All right, so to do that, clearly, empty set and the full set are there in theta. The empty set is there by force. The full set is there by definition of a basis. If you union all the elements of a basis, you get the entirety of the parent set. And what is theta? Theta is those things which can be written as the union of some of the members of B. In particular, if you union all the members of B, you get X, and therefore X is in theta. So this is clear. So let us establish closure under intersection. So for closure under intersection, let P and Q be arbitrary elements in theta. We want to show that P intersection Q is in theta. Want to show that P intersection Q is in theta. If P intersection Q is the empty set, then clearly it is there in theta, so I'll assume that this is non-empty. Okay. And now, by definition of theta, P can be written as the union of some of the members of B. So say P is the union of A alphas, where each A alpha is in the basis, and Q is the union of B betas, where each B beta is in the basis. So this is a complicated way of saying that since P can be written as the union of some of the members of B, we are just saying there is some collection of members of B whose union is P. The collection is indexed by some set J. This set J may be uncountable, who cares? Similarly, there is a set K which indexes some of the members of the basis such that the union is Q. And we want to show that P intersection Q is again in theta, which is to say that P intersection Q can be written as the union of some of the members of the basis. And to do that, let me draw a diagram first. So I have P, and then we have Q, and we want to show that this intersection is in theta. To do that, we just need to show that, or by definition of theta, we need to show that the union, this can be written as the union of some of the members of the basis, and to make that happen, to deduce that, we will choose an arbitrary point x in the intersection. We will show that there is some basis element which contains x and is contained here. Once we do that, then clearly we can express this intersection as the union of basis elements. Okay. Now, since this is the union of A alphas, x is contained in one of the A alphas. It could be contained in multiple A alphas, but it is contained in at least one A alpha. So let me draw that. So that is A alpha, and similarly it is contained in some B beta. So in writing, we will say that x is in A alpha and x is in B beta for some alpha in J and beta in K. Right? Okay. But now note that, or just by the choice of the A alphas, A alpha and B beta are basis elements, and thus there is some other basis element. There is Cx in the basis such that x is in this element and this is contained in A intersection B. So in pictures, this would what Cx looks like. This red thing. Once again, this is a basis element, that is a basis element, x is a common point in it. By definition of the basis, there must be some other basis element such that it contains x and is contained in the intersection of the two. So here I meant to write A alpha intersection B beta. Right? But this is clearly contained in P intersection Q. Why? Because A alpha is contained in P and B beta is contained in Q. So we have shown that around x there is a basis element which is contained in P intersection Q. This is there for every x. So formally, P intersection Q is therefore the union. You choose elements from P intersection Q and take Cx. The union of all these things will clearly be P intersection Q. And we have expressed P intersection Q as the union of some of the basis elements. So this shows closure under finite intersection, or closure under the intersection of two elements. So what remains is what remains is to show that we have closure under arbitrary unions. This is an exercise. It's easier than the previous one. The previous one was also easy, but this is even easier. So this shows the green thing in the previous slide, and that's it. That proves the proposition. Okay. Now, suppose we are given two bases, B1 and B2, meaning script B1 and script B2 are two bases on a set X, and tau1 and tau2 are the topologies generated by them. Then the following are equivalent. Tau2 is finer than tau1, which is a fancy way of saying that tau2 contains tau1. And the second statement is that I'll write something and then I'll say a colloquial thing, or maybe a more informative thing. For each B1 in script B1 and for each X in B1, there is B2 in script B2 such that X in B2 and B2 is contained in B1. So I don't like the fact that this has gone off the rails. Oh God, let me try to fix it. Hopefully this is better. Okay. So what is this saying? This is just saying that every element of script B1 can be written as the union of some of the elements of script B2. Let's be very clear about that. Just think about that statement. Why is this equivalent to that? Think about that. Every element of B1 is the union of some of the elements of B2. That's what this is saying. So the fact that tau2 is finer than tau1 is equivalent to that. And this is more or less an exercise using the previous proposition. Let me try to argue at least some part of it. Let's see why this happens. So assume 1, that tau2 is finer than tau1. We want to show this, which we just paraphrased in a different way. So fix an arbitrary element of script B1. We want to show this can be written as the union of some elements of script B2. Now, since this is there in script B1, it is also there in tau, because script B1 is contained in tau. Tau1, I mean. So this is there in tau1. And if it is there in tau1, it is also there in tau2, because tau1 is contained in tau2 by our assumption. Now, if it is there in tau2, what are the members of tau2? By the previous proposition, the members of tau2 are precisely those things which can be written as the union of some of the members of B2 or script B2. And therefore, B1 can be written as the union of some of the members of script B2. So I said a lot of things and you can fill in the details. And now for 2 implies 1. We assume the statement. We want to prove that statement. So let U1 be in tau1 arbitrary. We want to show that U1 is also in tau2. Right? That's what it means to say that this is finer than that. Now U1 is the union of elements from B1. Because what is tau1? By the previous proposition, tau1 is precisely those collection of those sets which can be written as the union of some of the elements of script B1. So U1 can be written as the union of some of the elements of script B1. And now each element of script B1 in turn can be written as the union of some of the elements of script B2. And therefore U1 can be written as the union of some of the elements of script B2. And therefore U1 is there in tau2. Let me argue the same thing. Let me repeat the same thing in pictures. So what we have is, we have U1. We have U1. U1 can be written as the union of some of the members of B1, invoking the previous proposition. Each orange thing is in B1 and together they exhaust everything. Now, if you pick one particular guy, let's say that one, this is an element of script B1, and by our assumption, this can be written as the union of some of the elements of script B2. So maybe we can denote that the diagram. So each green thing is in script B2. So what happened? This can be written as the union of the green things, and this is true for every orange thing. So this entire thing can be written as the union of green things. So U1 is the union of green things, but every green thing is an element of script B2. But an element of script B2 is also an element of tau2. So this U1 can be written as the union of some of the things in tau 2, but union of some of the things in tau 2 is also in tau 2. Tau 2 is a topology. So therefore U1 is in tau 2. So you can write that down. All of that verbalize can be formalized. Okay. Alright, so now we will prove a concrete statement. What I'm going to prove is really a theorem, but I pose it as an example. So recall the two metrics D2 and D infinity. And what we are going to show is that, so before I write down the statement, let me develop a notation. So or maybe I used this notation previously. So this denotes the set of all the balls with centers at points in Euclidean spaces and positive radii. Collect all those balls. Then we know that this is a basis on Rn, and we can also collect the same thing for the infinity distance. And we know both of them are bases on Rn. So what we are going to show is that both of these bases generate the same topology. That's very interesting. Then this set and that set generate the same topology on Rn. And this topology is called the standard topology. So this common topology that they generate, this is the standard topology on Rn. Okay, so by means of this example, we are also creating the standard topology on Rn. Sort of, we are just placing it there because this is the topology that we use unless we otherwise mention. So whenever the phrase Rn appears, or this notation, whenever we consider the Euclidean spaces, by default we will be working with the standard topology, unless in some special case we are working with some other topology. Then we will explicitly mention. Okay. So why is that? We will use the previous proposition. Basically, let's say tau 2, I don't know what notation I should use, but the point is this. If we can show that the topology generated by this is finer than the topology generated by that, and we also show that the topology generated by this is finer than the topology generated by that, then the two topologies must be same because both are finer than each other, and therefore they are the same. So that is how we will go about it. So what I'll show is that, so let me just develop this notation. So I'm proving the thing. So let tau 2 be the topology generated. Something is wrong with my iPad. Oops. Give me a second. Let tau 2 be the topology generated by the balls under the Euclidean metric, and tau infinity be the topology generated by the balls under the infinity distance. Whenever I use the word metric, I apologize, I shouldn't, even though they are metrics, but we haven't talked about metrics. Okay, so we will show, we want to show that tau 2 is equal to tau infinity. First, we will show that, or I will only show that tau 2 is, or tau infinity is finer than tau 2. So let us prove that tau infinity is finer than tau 2. And now since we know that both of these things are bases, we can invoke the previous proposition. So to prove this, by using the previous proposition, we will pick an arbitrary element in the basis that generates tau2 and show that if we choose an arbitrary point in this chosen element, we can find something we can find something in the basis that generates tau infinity which contains that point. Let me write that down in terms of pictures. So we will pick some arbitrary element in the basis that generates tau2, and that looks like this. Oops. That looks like that. Let's say we have the center, let's call it x, and the radius is, let's say, r. And this is dotted. I don't know if I can make it dotted. I can't make it dotted. So when I draw this picture, I mean the ball of radius r centered at x, and that does not include the things on the boundary. It only things which are strictly inside. So we picked some arbitrary element of that, and now pick a point. Let's call it maybe y. Pick a point y arbitrarily. Okay. What do we want to do? We want to show that there is some element of this which contains y and is contained in this original ball. The elements of this recall look like squares. That's how we can draw them in R2. So pictorially it should be clear. Squares can be fit inside circles. If you take this point in this circle, then a small enough square with y as the center will fit inside it, right? And that is basically the proof. That is how we are going to go about it. All right, so basically we want to show that there is some element here which contains y and is contained in the ball. So that is the next thing, and it's not hard to do. First, note that clearly the ball of radius, yeah, so let's say the distance between x and y is equal to something. Let's call it a. The Euclidean distance between x and y, I mean, that let's say that is a. In the figure, that is how we will denote it. Okay. And then clearly the ball of radius r minus a around y is contained in our original ball, and we are working with the Euclidean distance in this statement. This is the Euclidean distance, right? What is the idea behind that? We have this point y. If you draw this ball of radius r minus a, you will get this ball. With y as the center, you will get this ball. And you may feel a little bit of an itch because the boundary of this ball is touching the boundary of the outer ball. So, whoa, what is going on? Nothing is wrong here. But if that is bothering you, you can divide this by 2. Instead of r minus a, you can write down r minus a by 2. But this is perfectly fine. This is, yeah, so why is this true? This is true because of the triangle inequality. We did this kind of thing in the previous lecture, I think. So just use the triangle inequality. And what is the triangle inequality? Let me recall the triangle inequality. So the triangle inequality says that this holds for all x, y, and z. Right? And triangle inequality also holds for the infinity distance. This was an exercise. I proved the triangle inequality for the Euclidean distance in the previous lecture, but the other things were exercises. So if you just invoke that, you can prove this. And now recall that the infinity ball centered at y of radius scaled down by root n, that is contained in this. This is what we recalled in the beginning of the lecture. We proved this thing for n equals 2 in the previous lecture, and the general case was an exercise. So using this And using the above containment, we see this is the case. And therefore, indeed, there is a element of the second basis, or the infinity basis if you like, which contains y, and which is contained in the chosen basis element of the first basis, the 2 basis. And therefore, by the previous proposition, we have proven that tau 2 is indeed tau infinity is finer than tau 2. And by the same kind of argument, you can prove that tau 2 is finer than tau infinity, because we also know this containment that any ball under the Euclidean metric, again under the Euclidean distance with center x, is contained in the infinity ball with the same center and the same radius. In fact, this is true, right? This is true. So you just use that to argue the other part. All right, so very nice. We have now created a topology on Rn with which we will work. I mean, that is the topology which we will use to talk about continuity of functions between Euclidean spaces. So that is one takeaway from this example, that now if we are given functions between Euclidean spaces, we can talk about their continuity because we have created topologies on them, right? So in one shot, we have suddenly upgraded from just functions of this sort to functions of that sort. We did not need to build structures upon structures upon structures to get to n. In one shot, we have just suddenly upgraded to a great height. And this is only the beginning. Okay. Maybe I'll just complete this diagram here. I just wanted to draw this little square. And I want to be accurate. The way I have, this thing will look like that. Let me write it. So this square is that thing. Okay. Here is an exercise. So we have talked about the Euclidean distance and the infinity distance. This is another distance, another notion of distance. We will refer to this as the 1 distance or the L1 distance also. That is also how we may refer to it. The Euclidean distance may be referred to as the L2 distance. This is the L1 distance. And the exact same thing goes on. You can show the triangle inequality for it. I think it was already given as an exercise in the previous lecture. Okay. Or maybe it was one of the problems in the beginning of this lecture. So anyway, you can prove the triangle inequality for this. And you can create this thing, which is a basis. It was already asked. It says that it was already asked in the previous problem set that this thing is a basis. Show that this basis also generates the same topology on Rn. So we have yet another basis generating the standard topology. And what are the balls? What do they look like? I mean, what do these people look like? The balls of radius r around the center. You should draw them. What do they look like? Okay, so very important exercise. And now finally, for something very interesting, we are going to prove that there are infinitely many primes using what we discussed. It's quite amazing that we can prove something in number theory, something so number theoretic, using some elementary general topological concepts. And this proof is due to Furstenberg, a great mathematician. And without wasting time, let me start. So we will define a certain basis on the set of integers. So for an integer a and a non-zero integer t, define this set as the arithmetic progression with common difference d which passes through a. Right? So since d is non-zero, this is an infinite set. A is an integer and you're just jumping with steps of size d, but it goes on both sides. It's a very simple thing to understand, and suggestively we may also write this as a plus dz. Okay, so it's just a definition, and here is a small lemma, interesting lemma. Collect all of these arithmetic progressions, vary over all integers, and then vary over all non-zero integers. So you have collected all the arithmetic progressions, all the infinite arithmetic progressions contained in the integers we have collected. Then this collection is a basis on the integers. Okay, let's prove this. So clearly, if you take the union of the things here, you will recover all of the integers. One way to see it is that this is anyway all of the integers. So all of the integers is already sitting here. Okay. And we just need to verify the second property. So let S A comma D and S A prime comma D prime. Well, I shouldn't be using primes. This is also called prime. This is A prime, but we are also talking about primes in completely different capacities. So let's not get confused. So this is another basis element, and we will pick something in their intersection. Suppose there is a point P. P doesn't denote a prime or anything. It's just a point. Just some integer in their intersection. So we picked two basis elements. They could have not intersected at all. They could have intersected in the empty set. But let's say they do. Then to show that this is a basis, we need to find another element of script S which contains this guy and is contained here. But that one can just easily write down. So just consider note that P belongs to the arithmetic progression starting at P with the step sizes being the product of the step sizes here. Okay, and just note that this is contained in both of them, right? So P is already present here somewhere. So if you take step sizes of, jumps of this, you will always be contained here. Since this is divisible by that, if you jump with those bigger steps, you will clearly be contained there. So at any rate, just justify this for yourself. Very simple thing to prove. And that proves that this is a basis. We have proven our lemma. Okay, and now what we will do is we will equip the integers with this with the topology generated by this basis. So now Z becomes a topological space. Right? Okay. And here is a very simple observation. Note that every non-empty open subset of integers is infinite. So why is that? What are the open sets? If you have a basis, the topology generated by this basis can be described very simply. The open sets are precisely those sets which can be written as the union of some of the basis elements. Now, since every basis element is infinite, every open set has to be infinite. Every non-empty open set has to be infinite because it is the union of some of the basis elements, and every basis element is infinite. So this is there. This observation clearly holds. And another observation, every basis element, every element of script S is a closed set under this topology, of course. So when I say basis element, I just mean an element of script S. Okay, why is this? Here is one line argument. We have this arbitrary basis element. This is easily seen to be equal to that. Draw a picture and you'll see. In fact, here also draw a picture if that is not clear. If it's still not clear, take some special examples. Take d equals 2, d prime equals 3, p is equal to something, a is equal to something, and then just draw a picture and this will be clear. Same for this. Okay, so every basis element is a closed set. Now, here is the main point. If you pick anything other than 1 or minus 1, there will be a prime that divides it. What are the primes? The primes by definition are those positive integers which are greater than 1, whose divisors are precisely the number itself and the number 1. Those are the primes. So just by this definition, it follows that any integer which is different from 1 or minus 1 will be divisible by some prime. So now since this set is equal to that, we just argued this. So this is equal to that. If there were only finitely many primes, then well, what? Each of these guys is a closed set. Every basis element is a closed set. Each of these guys therefore is a closed set. And if there were only finitely many primes, this would also be a closed set. Right? Because this is a union of finitely many things, assuming there are only finitely many primes. So this becomes a closed set, and therefore the complement of this set is a closed set, which means that this is an open set. But then this would become a finite open set, and there are no finite open sets. So that gives the contradiction. That is the argument. So if there were only finitely many primes, then this is a closed set, and hence this is a finite open set, which is a contradiction. That's it. So beautiful proof of the infinitude of primes. If you unravel this proof a little bit, I think you will just go back to Euclid's original proof. But it's not so clear. I am always amazed by this proof. Okay, with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.